Okay, everyone, take a look at this image with me, because this is what you want to get really comfortable in reading. Okay? This is what will help you do 1.5, where it says, identify patterns of stability of isotopes and predict the likely mode of radioactive decay. So our objective today is that if I give you an isotope, you should be able to tell me, hey, that's radioactive, or, oh, it's stable. And if it is radioactive, what type of decay is it going to do? Is it going to do an alpha decay, beta decay, electron capture? What's it going to do to get stable? Okay, so this red line right here, this is our island of stability. If it's on that line, then it is stable. If it's not on that line, then it's in the sea of instability, and it's going to sail its ship to get to the line. Now, what we're looking at is we're comparing neutrons to protons, okay? So turn to your table buddy really quick and remind them, because they probably forgot, how do I find protons and how do I find neutrons of an atom? Ready, go. So there's this process. It's the first thing that they can study on how it's now, then they only give it a time. So this is like 180 or something like that. But then once it lasts long enough for them to actually learn a little bit about it, then someone gets to it. And it's crazy because they're still not lasting very long, but with the technology you have, with how long they do last, they are able to actually still identify like its mass. You can see they do have masses up there, as well as some of the neutrons. It does seem a little weird, right? It's like we never use them, we never see them. But I guess someone discovered that. Yeah, that will be, I mean, that's what I'm excited to see in the world of chemistry. It's so cool that we've discovered this technique, but I'm excited to see, like, will we get to a point where, hey, it lasts, and now look how cool this element is. Like, some of them, like, are really, really heavy metals. So, like, what can we use that for in terms of building structures, or stuff like that. But majority of them, yeah, some of the smaller new ones actually are usable. Like, americium is actually fairly stable. It's used actually in smoke detectors. Because it's radioactive, it helps in it, but it doesn't disappear fast enough that it's actually useful. So in a smoke, that's not my smoke. Is that my smoke detector? That's not my smoke detector. I think that's a smoke detector. I should know this. I guess it doesn't matter. But in a smoke detector, the basic idea is that radioactive sample is shooting out particles at a constant rate, right? And there's a detector on the other side that's detecting them. If something gets between it, it sets off the alarm. So when smoke gets inside, it can't detect the particles as well, and so then it sets it off. So some of them are useful, but I agree, a lot of them it's kind of like, what's the point? And I think it's just that of like, well, what could it be? So, great question. Okay, someone by raise a hand, volunteer your neighbor to answer, how do I find number of protons? So you're raising your hand for your neighbor, not yourself. Oh, that was quick. I don't know who, I think Jackson was first. That means you're answering card. So how do I find protons?
Protons, it's going to be the blue number on your
Perfect. Have a smiley face for that. Okay, blue number, atomic number, number of protons, it makes the atom what it is. Right? That's why, like, the theory behind making new atoms is very simple. Right? If I wanted to make 119, theoretically, all I have to do is just put a proton in that element, and it becomes 119. The actuality of the experimentation is very, very difficult, right? Actually getting a proton into the nucleus, keeping it there, making it stay is very, very difficult. So, okay, someone else volunteer your neighbor to tell us how many neutrons something has. Well, you're all too nice. Okay, how do I find neutrons? You got it, Emily. That's what happens, right, when you get called on. So we know this is protons, so I have protons as the blue number. Where do I find the neutrons though? Oh, it's related to the red number. You want to help her out, Michaela?
Yeah, sure. Don't you mind if the blue number from the red number? Or is it the red number from the red?
Red from blue, technically, but you're on the right track.
All right.
Now, technically, it's not the red number, but it is related to it, right? Yeah, Rachel.
Take the mass of the atom and then subtract it by the number of protons.
There you go. So the thing to remember, everybody, is that mass of an atom is all about its protons and its neutrons. Because remember those little tiny electrons on the outside? Teeny, teeny, tiny. They have zero weight in comparison. So the mass of an atom is all about the protons and the neutrons. So you'll always have the mass, and you'll always have the protons, so you just have to do a little step of subtraction to find how many neutrons something has. Okay, so let's go ahead and do a problem right here, and let's find whether this isotope is stable. I don't think this is on your paper, so if you want to just write it in somewhere, but I want to practice it. Okay, so let's test. Let's do the one I just said. So we'll do americium. So 95, and let's do, okay. So the question is this, the first question is this isotope stable or is it not stable? So we know how many protons it has. Okay. How do I find its neutrons? Good, so take 243 minus 95, what do we get? That sounds right. $148?
Yeah, 148.
That doesn't make sense. You put it in your calculator? 148? Okay. Oh yeah, that makes sense. It's just a little off 100. Okay. Protons, neutrons. Now here's the biggest mistake I see made. Is students will just take these two numbers and throw those on the graph. You've got to find the neutrons. So now we go to 95 protons. So I'm about right here-ish. Okay, and then we're at 148, which is off my graph. I picked a bad example, but we can go with it anyways. Okay, and then if I connect those two, we would see where it lines up in terms of our line of stability. Now this graph obviously keeps going theoretically, right? And so we can see where it falls. Let me pick one that lands on the graph this time so it's easier to tell. Let's do aluminum.
27.
Okay, so once again, proton number. Neutrons would be 17. Line it up on your graph. So 13 and 17. Pretty close, right? Pretty close. So either it is stable, or if it wasn't, what type of decay is it going to do? A beta decay. So remember, this is the sign for beta. Okay? If it falled over here in the purple range, then it would do an electron capture. How does this image look without colors on yours? Can you see the difference between those bottom two? Oh, good.
There's a line.
Okay. I wasn't sure how it printed without color. And then over here would be alpha decay. Now the other thing this brings up is what is known as a decay series. If something lands all the way over here, just doing an alpha decay is not going to get it to the line. So it's going to go through alpha and maybe multiple alphas, and then electron captures to get up to the line. So the other thing we'll do in our assignment today is practice these big long sequences of, okay, it's going to do this, Now it's going to do this and watching the change it goes through. So, questions on interpreting this graph. And once again, that's what we'll practice on our assignment today. So, if you understand it, but you're like, I'm just not sure, we'll get more practice with it. Okay, this one is actually just review questions. So with your table, buddy, for 4 smiley faces, fill in those blanks of those 4 practice problems. Ready, set, go.
Do it.
Fill those blanks.
This bottom number is the.
I thought. When you're done, set your pencil on your paper. Okay, everyone ready to check? Okay, for each one that you get correct, you can have a smiley face for. So this first one right here, you should have 92, uranium 235. Questions on that one? Now someone just remind me, why did the element change? Because the protons change. If protons change, we make a new element, right? Okay, this one you should have 26 on the top, 44 on the bottom, which gives us that.
What?
26 doesn't even make sense. How can you have a mass of 26 when you have 43 protons?
So it's 40.
It's a plus one, not a minus.
Oh my goodness. This is a plus?
Yeah. So it's a beta. It's a beta.
It's a positive, right?
So that's a positron, yeah. So this should be 42,
Yeah.
which means it's molybdenum. It's just an element. Okay, thanks for clarifying there. Did I mess up any of my other numbers before I saw the other ones? They look okay. Okay, so this one should be 122. It should be 51, which makes it antimony. Okay, and then this one, 192, 77, uranium. scandium or something like that? IR. Go ahead and have a smiley face for each one you got correct, so up to 4. Questions? Yeah, McKay. So, yeah, so it sounds like a lot of you made a similar mistake as one another, right? Where you forgot to pay attention to where the arrow was at, and so you did it in the other direction, I guess. So, hey, but remember, be happy you made that mistake today, because on the test next time, I guarantee you're now going to think twice where the arrow is, right? So, mistakes are good. Any questions on that? Okay, we're going to watch one other short little video, and then we'll do our activity on the computers to practice all this.
Everything okay?
Regular service helps you stay safe on the road. But if you get injured because someone else wasn't as careful, call Craig Swap and Associates for the 5-star service you'll need to win your case.
Is that weird?
Craig Swap and Associates. One call, that's all.
I like to hit my mute button to try to mute the commercial. I won't.
You probably already know that everything is made up of little tiny things called atoms. You might even know that each atom